Here is an SDR play. It's connected to this signal generator at 229 megahertz. Right now it's switched off because I'm listening to the noise floor. And the noise floor doesn't seem quite clean. To investigate that, I have another receiver that is listening on this point. Now this capacitive probe is connected, it's coupled to the signal generator side, and the ground point is here. And I look at the screen of the other receiver. And you can see the noise floor. It's around, what is it? I placed the mouse there, and it's 41.5 dB or so. And then I move this capacitive probe to the other side. To listen to the noise on the USB cable. And indeed, we see there is a noise signal there. I am running HD SDR, and I have set the default parameters with one exception, that I have disabled the AGC and set the suitable volume here. You can see now the S meter shows, what is it, plus 17 dB over S9. And I switch on the generator, and to get 20 dB more. That's maybe 1 dB too much. I remove 1 dB. The level then is minus 109. And that means that the power of the generator now is minus 109. And then for the bandwidth, which is 2.5 kilohertz, that's 34 dB. And then 20 dB because of the signal to noise ratio that I could see on the S meter. It sums up to a noise figure of 11 dB at minus 163 dBm per hertz. I converted a part of the USB cable to an inductor, 3 turns, and now the signal sounds cleaner. And if I look at the S meter and switch off, it's clear that it's more than 20 dB. I have to turn down the level a bit. Maybe like this. So now the level is minus 115, and that's, is it 6 dB better than before? So 115 plus 34 plus 20, that's minus 169 dBc per hertz for a noise figure of 5 dB. So it is much better. And it's just this inductor. So I have the other receiver as a reference point on the signal generator side. And then this is the noise floor. And I move it to here. And you can see what is the noise level on the radio side of the inductor. And then I move it to the other side, here. like that. And you can see the noise level is higher. Conclusion is that noise is coming from the computer on this cable, but it's also coming out from the USB chip inside the SDR Play. I removed the coil, and now I demonstrate another way of inspecting the problem with this radio. I just tune it to the FM band, and here is the local Sveriges Radio program 1, one of the stations. It is not particularly near here, but it's strong. If I listen, having interference from the computer traveling up the cable, or having the cable picking up the local field from the local FM station, sends energy into the input circuits of this. It's connected like that. I have connected the network analyzer, putting the ground here, and looking at the impedance on the ground of the USB cable. And this is what I see. And as it turns out, the impedance is very high on the FM band. Knowing that the impedance is high, I have now connected this other generator, set it to 100 microvolts on 90.4, and I find then that the signal here is approximately the same level as the local FM station. So 100 microvolts of interference on the USB cable would be very bad for the performance of this radio. The noise levels I see are much lower than that, but nevertheless there is a problem on many frequencies with interference from the USB cable entering the box. To reduce the problem, I have wrapped the radio in aluminium foil, making sure there is good electric contact here on the antenna side, as well as here between the aluminium foil and the outer ground of the USB cable. What I see now is nothing of the local FM station. Here, well, some fragments when it occasionally is unmodulated. The signal generator looks as strong as before, but now it is on 100 millivolts. That is 60 decibels more. I have gone back to 230 megahertz and switch on the signal generator. And as you can see on the S meter, I now got 20 dB signal to noise ratio. And the signal level is minus 117. That is 2 dB lower than I had before. The S meter is not very accurate, and I don't know if there is a way to get a digital readout on this program. I will show it in Linrad a little bit later, where I know better how to get the information I'm interested in. Anyway, there are some possibilities with the SDR Play. I can change the IF bandwidth, let's say 8 megahertz, and then the sampling rate goes up to 8 megahertz automatically. And that's fine. I can, of course, change the IF gain but it is high. I'm now looking not for dynamic range, but just for sensitivity and noise problems. I have reduced the IF gain and set a very strong signal, minus 50 dBm. And it is here, and I will step the frequency. And here comes the aliasing. And now it's gone. So with 8 MHz IF bandwidth, aliasing is present up until approximately this frequency. I can change the IF bandwidth, make it 7 MHz, and then the scale changes. But I didn't want this. I want 8 MHz sampling rate. And the aliasing should now be a little bit weaker. I go back to 8 MHz bandwidth to see the difference. And the difference is very small. To be able to use Linrad, I have to replace the driver. The HD SDR uses the MSI 2500 driver from Mirix, but I replace it with the Win USB using Zadig. I launch Linrad and set a standard configuration. Normal user, that's S. Enter. Font scale. To make the video easier to see, I make a fairly big font. I make font scale 3. You can use Windows fonts, but that's more elaborate and I don't want to go into that. Process priority normal, and screen size I want it in percent, so I say no, and let's use 75 width and 75 of the height. The required DLL package number 3 is installed. That's the message that I get here. And I press W to save. First I have to click and then press W to save this. And U to get into the setup. And input A. And I want the SDR play, that's I. And here I can select different formats for the USB transfer. And it seems reasonable to select number 3. And 0EIF, because I want a wide bandwidth. And the widest is H, 8 MHz. Sampling speed, well, I can set 8500 kilohertz, adding zeros to get it in hertz. Crystal error, I don't know anything about that. Output B. Use port audio? No. And I use the speakers on this computer. X and then W to save. And then I go to the SSB mode, that is D. And there are no parameter files yet, so I have to set up things. With 8.5 MHz bandwidth, I cannot have 100 Hertz resolution on FFT1. I make it, let's say, 2 kilohertz. That results in an FFT1 size of 8192, 2.075 kilohertz bandwidth. And I want an efficient FFT implementation. First forward FFT version. The fastest one is number 4, and that's available on this computer. It's going to use SIMD. That is single instruction, multiple data. It's a multimedia kind of instruction, and it's going to use it in parallel. That's not available on all hardware platforms. And I can split it in more than one thread, let's say 2 threads. And this might be okay. I press enter. And enter again. First mixer bandwidth reduction. I don't want to reduce by as much as that. I make it, let's say, 8. And enter. And here we go. This is the SDR play on 97 megahertz at a very low gain level. I make it maximum, and then we get a very high noise floor. And I can see the leakage of the local FM station here, and here, and here. Let's go for 142 megahertz as the center frequency. So I have 144 up here. And I inject the signal on 144.15 at a low level, and I do it through a directional coupler into the SDR play. Switch off that signal generator, and we don't see much, but we do see it. It is here. I want to see it better. It means I increase the contrast. That's 1 here. And then I have to change the 0 point, let's say 50. And even that is not good enough, 70. The signal level is very high. That's not really very good, so I make X. And then P. And then I change the first FFT amplitude here from 2000 to, let's say, 5. And then the spectrum is at a more reasonable level, still very high, but I have to put here maybe 40 or 35. And now I can see pretty well the weak signal through the directional coupler. I switch it off and I switch it on. And I click on that signal and we can hear it. And now I reduce the gain until signal to noise ratio is degraded. We have the signal looks like 20 dB above the noise in the baseband with the current settings of the baseband bandwidth. So I reduce, and as you can hear, the signal disappeared completely. This is a bug in the library I have to select the frequency again to tell the SDR Play that we want to listen to 144 and not to another band. So I have to change that to start with. As it turns out, it was easier to change Linrad than to change the library. So now it is the version 04.11 preliminary. To see better, I expand the scale. Here you can see the signal. And now I reduce the gain until signal-to-noise ratio degrades. I want it to degrade to about 20 dB. Oops. Well, it's about here. Now the signal-to-noise ratio degraded significantly. It means that I should have the maximum dynamic range. So I switch on the strong signal. 144.5 megahertz and 0 dBm. That's too much. Here is approximately the maximum level. This is too much. So I have minus 35 dBm. That's when the unit saturates. When set for a gain that reduces signal-to-noise ratio significantly. If we look at the signal-to-noise ratio, as you can see it here, and I switch off the strong signal, you can see that reciprocal mixing is actually the limiting factor. The strong signal, 144.5, goes through the directional coupler into the SDR Play. I can see it here. And I have set the S-meter calibration to place it at 0 dB, 0 dBm. Now, if I increase by 1 dB, I get a lot of extra spurs. That means I'm in saturation. So back, now it's not saturated anymore. The weak signal, 144.15. It's somewhere around here. I switch off the strong signal to see it easier. And 144.15. This is an easy way of tuning. It's here. And on the S-meter, I don't want the peak, I want just the RMS, that's the yellow track. It is about 91 dB below the strong signal. and I switch it off to read that the noise floor is about 99 dB. I have to wait for it to move like this to read it out. 99 dB, and it is in a bandwidth of 1 kilohertz. It means that the noise floor is 99 plus 30 means 129 dBc per hertz. At a separation of 350 kilohertz. So I switch on the strong signal again, and then we can see that reciprocal mixing degrades by about 6 decibels. I'm running at 9.5 megahertz. It's a little bit too high. You can see glitches occasionally. And from the spectrum we can see that the noise sideband extends this far, but if I go down like that, there is less reciprocal mixing. I switch off the strong signal. It's a modest difference.